This is a review of questions involving in combustion analysis. There's two issues that you should be aware of. Is that in a simple combustion analysis problem, only carbon and hydrogen are present. In a more complex problem, the presence of a third or more elements can complicate the calculation. So here's an example of a question that contains only carbon and hydrogen. The following example contains only carbon and hydrogen. Researchers used the combustion method to analyze a compound used as antinaught additive in gasoline. A 9.394 milligram sample of the compound yielded 31.154 milligrams of carbon dioxide and 7.977 milligrams of water in the combustion. Calculate the percent composition of the compound. So the first thing I did was to assume 1,000 times bigger experiment. Why? Because it allowed me to turn the milligram amounts into gram amounts. In a combustion analysis, we have a compound, we burn it with oxygen to produce carbon dioxide and water. Here are the gram amounts that we would have generated if the experiment was 1,000 times bigger. I also encourage my students to write the molar mass of carbon dioxide and water at the top right of their paper, because they come up often enough that it's good to memorize them. And if you write them a few times, you will end up memorizing them. So you had 9.394 grams of the sample, and it produced 31 grams of carbon dioxide, 7.9 grams of water. We divide by the molar mass of each. We get the moles of carbon dioxide and carbon, because for every 1 mole of carbon dioxide, there's 1 mole of carbon. We multiply by the molar mass of carbon to give 8.5 grams of carbon produced, or present in the original molecule. With water, we have that many moles of water. We multiply by 2 to find the moles of hydrogen, because every mole of water contains 2 moles of hydrogen. And then we reconvert back to the grams of hydrogen by multiplying by the molar mass of hydrogen to give 0.89 grams of hydrogen. When we add these two numbers together, we should get this number if there's no other elements present. And that's exactly what happens. We added these two numbers, we got 9.395, which corroborates the fact the original sample weight, which tells us there are no other elements present. We then take two possible courses of action. We either assume a 100-gram sample after calculating the percentage composition of the compound. So we have 8.5 grams of carbon divided by the total mass of the sample times 100 gives you 90.5% carbon. The rest of the mass has to be hydrogen, so we get 9.5% hydrogen. We then assume a 100-gram sample, which turns the percentages into gram amounts. We divide by the molar mass of each element, and it gives you a mole amount, which we then divide by the lowest number of moles to give a ratio of 1 to 1.25. I then multiply that ratio by the lowest integer value that will result in a whole number, because you can't have half atoms in a molecule. And the empirical formula ends up being C4H5. Alternatively, we could have used the original amounts of moles calculated in the problem to establish the ratio, and it would have given us the same ratio, 1 to 1.25. We would multiply it again by 4, and we would get the same result, just the final answer. In the next question that I approached, there's more than one element. There are more than 2 elements in there. There's carbon, there's hydrogen, and there's also oxygen. So we wrote the formula of the molecule with X, Y, Z to represent the numbers for the integer values of the amount of element present. We reacted with the oxygen because it's a combustion experiment. We produce CO2 and water. So we calculate how many moles of CO2, how many moles of H, and that turns into grams of H and grams of C after the appropriate conversion factors. Then what we do is we take these two amounts, add them together, and we subtract them from the original weight of the sample. The remaining weight, the 0.133 grams that's left over, has to be the mass of the oxygen. We then, again, can have two ways of solving it. One is to use just the moles that we calculated in the original experiment, or we can assume a 100-gram sample, which is what I did. 40 grams by the molar mass of carbon present in the sample gives you a ratio of 3.33. We get 6.66 for the ratio of moles of hydrogen, and 3.33. So that 3.3 to 6.6 to 3.3. If you divide everything by 3.33, you get a ratio of 1 to 1. And that is the empirical formula of our substance, C1H2O. Lastly, we had a solution equation problem from our homework where we were asked This is from Brown, 10th edition, page 141 or 43, I believe. Problem number 461. It's a 2.2 molar solution of nitric acid, and there's 35 mLs of it. How do you find how many moles of nitric acid? Well, you simply multiply the volume in liters times the molarity. Liters will cancel, and it gives you how many moles of nitric acid is present.